All right, you are live.
Yay.
We did it. What have we done? It snowed yesterday. Like we got another 10 centimeters. No, maybe 5 centimeters of snow. 5 centimeters of snow.
Is that typical for April?
No, this is madness.
Canada can get
Florida,
snow in
Canada.
June, as far as I know.
Florida of Canada.
Okay.
Yeah. I feel like I'm pretty consistent about that. But I am just getting hilariously embarrassed about that. Yeah, it's been. I can't even. I don't even have words. Like some kind of changing climate is the way I would describe what's happening to us here in Western Canada. Where the summers are too hot. It's just snowing all day. Yeah. The summers are too hot. The winters are too cold. It's not right.
Sorry to hear that, Fraser.
Yeah,
I'm really enjoying this warmth over here.
Are you guys on the East Coast? You guys are getting fairly warm weather out there?
Yeah, the last 2 days have been gorgeous, like 70 degrees and sunny with a light breeze. It's really nice.
That's like
I missed that.
Yeah.
High teens. Yeah, that's nice.
Yeah.
Yeah.
It's like denim jacket weather.
I mean, we're bilingual by temperature in Canada. Or sorry, we can understand both metric and imperial most of the time, but that's the one that we have no connection to. Well, that's not true. You'll set your oven to 375, but you'll measure your temperature in like outside in Celsius.
Interesting. It's a weird
Yeah.
medium zone.
Yeah. Yeah, I don't know. It's weird. Is Amber? Oh, there you go. Amber was frozen for a second there. Okay. Yeah. No, I've mentioned we're completely messed up. You buy your apples by the pound. You buy your meat by the 100 grams. You measure, you know, we call it a foot-long Subway. Trying to think. Buy your gas by the liter. It goes on and on and on. We're really messed up. People say, "Oh yeah, Canadians, you guys are in the metric system."
Is it a quarter pounder at McDonald's?
Totally a quarter pounder. What is it? We're like a Pulp Fiction. We don't know what a quarter pounder is. No. Yeah, we totally have a quarter pounder. All right. I think we've reached the time. It's the 5-minute mark, and I think we've got a lot of news to get through today, and possibly an argument. So I think we're going to want to get cracking here. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, April 13th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, I don't even know what this means, Carolyn. Creep on the moon. You're going to have to explain this when we get there. Neptune is cooling down and scientists don't know why. Magellanic Clouds smashing together, forming stars, and the private space station crew Axiom 1 arrived. What does it mean? Is it a good thing or a bad thing? Joining me this week, let's see. We've got Moya McTeer, Dr. Moya McTeer.
Doctor, for almost exactly a year. I just had my doctorversary. It was really nice. I ordered Thai food because that's the food that got me through my PhD.
So is this now going to be your thing?
Yeah, every year. Why not celebrate with a little bit of Thai food?
That's great.
Yeah.
The space industry is just filled with these kinds of what do they call them? Like with the peanuts, or when they they have like peanuts at like a JPL land. Yeah, these strange traditions they do in the space industry.
That's nice. Yeah.
And this is how it starts. So now all doctorates will be eating Thai food on the anniversary.
Mm-hmm. You hear that, Marie?
Now.
Remember this.
Yeah, it'll turn into.
It seems you started something big.
Yeah, exactly. Yeah, defend live, eat Thai food.
Yes.
This will be your legacy. We've got Carolyn Collins-Peterson. Hey, Carolyn.
Hey there. Hey, from snowy Colorado.
Are you lacking
and
a
I just
spring
want to say
well?
that when I was working on my master's thesis, I drank a lot of root beer.
Delicious.
So that's another thing then. Yeah, all kinds of traditions here. All right. So joining us, we have a new co-host. We got Marie-Liis Aru. Marie, welcome to the Weekly Space Hangout.
Thanks for having me.
So people don't know who you are. So why don't you let us know something about you?
Yes. So first of all, my name is Marie-Liis Aru, but feel free to call me Marie. I'm from Estonia, a country in Northern Europe, but I'm currently based in the Netherlands. I recently traveled back to Estonia, which had also a lot of snow, like tons of snow and hail.
Okay, I don't feel alone then. All right.
But yes, I'm back in the Netherlands, and in here, in the contrary, we have the tulips blooming and just a lot of flowers everywhere. Yeah, really nice.
And what's your specialty? If people are, what's your beat?
Yeah, so I have my degree, my master's degree in space sciences, but I focused more on planetary science. And after that, I carried out research at the European Space Agency in the Gaia team. So the Gaia is known for the
awesome.
Galaxy mapping. Thank you. Gaia is known for this great galaxy mapping and creating this immense chart of the stars in the Milky Way galaxy. But my research was actually quite different. And I used data from the attitude control system of Gaia. And I used this data to trace back how extremely fast tiny particles called micrometeoroids were affecting Gaia.
Really
that's kind of a really interesting take on how to use all of the data that's possible. All kinds of bits of data that we get back.
And I guess you could imagine that's going to be interesting for James Webb, which is out at the same spot, the same Lagrange point as Gaia, but it's a much bigger surface area. What kind of impact, pardon the pun, will all those micrometeorites have on the James Webb throughout its lifetime?
Exactly. So I hope to get my work published this year or next year, and then we can draw parallels of this, of the two missions. But then for all future missions, that will be launched to Lagrange 2 point, which is really exciting.
Yeah. Well, fantastic. Well, welcome aboard. And
Thank you.
I can already you've got lots to teach us. So we will get to your stories in a little bit. But before we do, I want to give a huge shout out and thanks to our good friends of the Weekly Space Hangout crew. They're our friends, our fans, our executive producers. They call the shots. We do what they say. And if you want to join that incredible community, totally free, go to wshcrew.space. They will hook you up with all of the credentials you need to bring on special guests onto the show. And speaking of special guests, we've got Amber Dubill. Amber, welcome to the Weekly Space Hangout.
Hi, happy to be here.
The question I always ask people, who are you? What do you do?
I'm a mechanical engineer for Johns Hopkins Applied Physics Laboratory. We do a lot of things with various spacecraft you might have heard of: DART, Parker Solar Probe, IMAP, and throughout my schooling and now as a mechanical engineer, I now have developed expertise in diffractive solar sailing. So that is where I'm pushing the boundaries.
So Amber, you're totally dropping out here. We're only getting a fraction of what you're saying. And now you're frozen. Yeah. So we're gonna try and get this sorted out technologically, and we'll see if we can fix this. So I guess Amber said she might stick around for the whole show. So I guess we're gonna do this in a completely different order instead. Do I want to have the argument first? We don't know how long this is going to last. So why don't we instead, Carolyn, I have no idea what you're talking about. What is Creep on the Moon?
Well, Creep on the Moon is a story that came out this week about the moon, obviously. And I saw lots of people writing about the two-faced moon and the double-faced moon and all this. But what it really aims at is to talk about why the moon seems to have a two-sided dichotomy. That is, each side of it looks different. And that really leads to a lot of questions about why that might be. And that's a mystery that planetary scientists have been working on. So the first image that I have is one of the far side. Are we going to see images here?
Pamela might be doing technical support for Amber. Amber, how are you doing? Can you move? True. Can we hear you?
You see me? Do you hear me? I was following up right until that moment, like right until they're like, okay, you go.
Yeah, you think you're just gonna have to keep stretching and stretching. All right, well, we're gonna let Carolyn finish the story, and then we're gonna continue on with the interview with you, and maybe by that time, the internet will have settled down. Settle down, internet.
Okay, so what we're looking at here is the near side of the moon, and if you look at it closely, this is the one we're familiar with. It has these lovely thick lava plains. They're called maria, which is the Latin plural for the word ocean, and to the ancients, these look like oceans on the moon. So the big question is what caused them to form, and there are a number of theories about it. Going to planetary science myself, we went through a number of them where we thought, well, maybe it was giant impactors or something else happened to the moon. And then all around the lava plains, you see a lot of cratering, and we know how cratering happens. Stuff smacks into the moon. And it digs out craters. And we know that the moon got many of its craters during the late heavy bombardment, which is a period about 3.8 billion years ago, where Earth and the moon were really being bombarded with a lot of debris left over from the formation of the solar system. So any craters that you see in the lava plains actually happened after the lava flowed. So if we switch over to the next image, which is the far side of the moon, that really remained unseen by human eyes until the space age. And since then, now we've managed to map it, to take a lot of images of it. You can see pretty well that there are a lot of craters. Pamela, can we get the second image, please? And you can see that when we do get to it, that there are very few mare, very few of these lava plains on the far side of the moon, but it's tons of craters, just very heavily cratered. And so that indicates that, like the near side, it was bombarded billions of years ago, but nothing happened to flow over them. So the big question, why is the answer is in an area that's on the far side of the moon called the South Pole Aitkin Basin. And it's a huge impact basin. We can't see it from this side. We can see an edge of it from the near side. And it's one of the largest impact basins we know about. It's 2,500 kilometers across, and it's very deep. In some places, it's 8 kilometers deep in some of the deepest parts. And it probably formed about 4 billion years ago. And the big question is, what happened? Well, something big smacked into it. A slow-moving object. It did not move very quickly, but it plowed into the moon, and it didn't just form this basin. That impactor set in motion a whole lot of other activity. So think of it this way. The force of the impact melted a lot of lunar rock, and that launched a huge plume of heat that moved through the inside of the young moon. Now, the young moon had a fairly dense magma ocean just beneath the surface, and this plume of heat basically moved all the way through the moon, through this, what was already kind of a molten subsurface, and at the youngish moon, and it convected through the lunar core, and the plume brought a whole lot of materials with it, like the element thorium, we had potassium, we had rare earth metals, we had phosphorus, and a number of other metals, and those all kind of congregated to the near side. Now that combination of those metals is called CREEP. So it's an acronym, KREEP. K is for potassium, REE is for the rare earth metals that were carried along, and P is for potassium.
Now I understand.
I'm sorry, as phosphorus. Yeah. So those were all deposited on the far side in an area called Oceanus, Procellarum Oceanus. And people have long wondered why this area had such a high abundance of these CREEP materials. And so this kind of explains why those would have been deposited there. What I really like about this story is that the model, the model that they put together.
All right, I'm done with the internet.
Together a computer mare, you have this heavily cratered area basin, but you're also coupling it with something you don't see unless you're using spectroscopy or you're studying the chemical elements. You're basically coupling it with chemical composition, particularly in the Procellarum region. And then you wrap all that up with what you know about the young moon. And all of that is to explain this really strange anomaly that shows up in Oceanus Procellarum. That's really sort of the whole point of the story.
So, I mean,
it's CREEP.
When you look at this impact, it's this giant impact right almost at the very bottom of the moon. Is it because it was slightly off center that you got the two hemispheres looking so different? If this had smashed into like the one side, would it have looked very different?
Probably so. I mean, it was a very slow moving impact. It was also an angle and hit that area. You can see the edge of the South Pole Aitkin from the near side of the moon. I mean, you can see it if, depending on libration, you can see this, but the most of it you can actually only see from the far side. There is another, trying to remember which body it is in the solar system that was smack on sort of at the equator, and you see a lot of damage on the far side. I'm trying to remember which
at the antipode. Yeah,
I think so. Yeah, and so
Mercury?
Basically something hits on one side and yeah, I'm trying to remember, but
yeah,
you get.
I think it's Mercury. Yeah, you get these ripples go through the rock, and then they combine on the other side. And they think that might have what happened here on Earth with the Deccan traps. That you got this giant impact on one side, it propagated through the Earth, splashed on the other side, and caused this jumbled volcanic terrain on the other side. We would see something similar on the top of the moon.
That'd be interesting to look at. I think the one thing that struck me was that because this happened when you had the moon had a relatively thick molten layer, that probably affected what you were going to, what was going to happen at the antipode, on the opposite edge of where that would happen. But so with the convection layer, basically this heat convected through and just brought this creep material to one spot in the Oceanus Procellarum.
And Pamela's saying Pluto too.
Chemical.
Yeah. Yeah.
Say that again?
It's amazing when you think about the fact that when we look at the moon, we see all those mare, and then when we finally got an orbiter out there to see the far side of the moon, it was just this weird crater. Can you imagine if it was the reverse? If we had always seen the cratered side of the moon, it just looked like Mercury, looked like any other place in the solar system, and then suddenly we got a chance to see the far side, and it was these weird lava oceans and stuff. It would be such a bizarre thing. So I'm sure we were expecting.
Well, and the
Maria
Maria
like
actually probably formed as a result of this. I mean, that's not one of the hard conclusions in the story, but it is suggested that these Maria may have formed as a result of this, and they still don't really have a good answer. This may be part of it.
Yeah, I mean, we've heard, I think every year or so we get a new theory on why the moon has a different look on one side than the other side, and this is the latest version. I mean, I'm going to add it to the pile when people go, why does the moon look differently? Well, it might be this, it might be that, because the one that I've heard is that the moon got hit, or that there was like two moons earliest on, and then one recombined and sort of got mushed into one side of the moon as they formed. But anyway, it's cool to see and I think we need to send astronauts and set up a base down at the South Pole, and they need to dig rocks and need to do some research.
I think what ultimately it's going to be is a combination of a lot of the different answers, and also once we get a lot more samples, because the sampling is still pretty incomplete on surface samples.
Yeah, really fascinating. Very cool. Thank you, Carolyn. All right, Amber, I see you moving continuously this entire time, so I've got to think that your internet is going to hold. Unfortunately, all we got was the occasional word. I'm going to have to ask you to do it again. Who are you? What do you do?
I'm a mechanical engineer for Johns Hopkins Applied Physics Laboratory. We might have heard of us. Worked on Parker Solar Probe, DART, IMAP, now Dragonfly, as even New Horizon, Messenger, had an instrument on ESA's solar orbiter. Lots of cool missions come through here, and I particularly worked on DART and with double asteroid redirect tests, which is funny because you just talked about impacting the moon, and obviously DART's going, and if you've heard about it, it's going and hitting an asteroid on purpose. So to actually explore
which part of the mission? So which part of the mission did you actually get to work on?
I worked on the hinges for the deployment of the solar arrays. So they have these rollout solar arrays, ROSA, and I worked on the hinge mechanism, which actually was heritage from another spacecraft called Timed, which was in like the 90s. So that was we reuse, and recycle, and spacecraft is the fun part.
And I don't know if you've heard the Lucy mission, they haven't been able to open up both of the hinges on their solar arrays. So it's possible that they didn't get the right old technology on their spacecraft. So how does this hinge work?
The hinge actually has it's a spring. So it has these like very specific springs that you have a damper. So when you remove the launch lock, the springs will slowly start to open it up, but you actually have like good amount of torque on them, so you have to have a damper so that it's not like just flipping out there, right? Like you want a very nice slow deployment, and that's the same with I work more on IMAP because DART's out there, DART's gone, DART's gonna hit in September, and I've done way more on IMAP, interstellar mapping and acceleration probe, and that's going to launch in 2025. And we have a deployable of a mag boom and some instrument doors, and same thing. You don't want deployments in space to be fast. And then leading to that, I most of my expertise is actually in diffractive light sails, so solar sailing, through my thesis, through my graduate experience in NIAC and Innovative Advanced Concepts grants at RIT, and now trying to at Johns Hopkins. And those deployments are also super slow. So yeah, that's the deployment I'm talking about there. So that was actually NeoScout.
Now, when you say slow,
so this,
what is
so
slow?
if you're talking about slow, this is NeoScout. So this is a solar sailing mission, near Earth asteroid scout, through NASA Marshall, and they partner with us on diffractive light sails, and our NIAC awards, and we were able to go out. So that entire sail is like the length, both sides are like the length of a school bus. So it's hard, it might be kind of hard to see in that picture. And then that picture to the left, that's it, all stuffed in that, and that's like the size of a shoebox, not even. It's a CubeSat.
Wow.
And it took,
that's amazing.
We were in this huge clean room down in Huntsville, Alabama, watching this. This is the last deployment of their test, last deployment of their sail before it got packed away for good. And it was, I would say, an hour. It took an hour to do it, at least. So you don't want to have a lot of you don't want to be sending yourself tumbling or sending yourself, in wild directions, because you're exploding a lot of energy, right? So any deployment is a lot of energy that you're now introducing onto your spacecraft. Attitude control.
I mean, we think about James Webb and all of the hundreds of actuators that had to go one after the other, all of the explosive bolts that had to release, everything that had to go to get that entire spacecraft into its final enormous configuration. But packing a solar sail into this tiny little box, like, I don't think you've got actuators there specifically. What is the way that you're going to get it from tiny CubeSat to fully deployed school bus sail?
So it's kind of funny, because if you look at all of the solar sailing missions that have existed, right? So there's Icaros was the first one, and that was very different. The mechanism that they used is they actually spun out. So they put masses on the sides on the four corners of the sail, and then they spun the entire spacecraft to like deploy it out, right? They used centripetal force. What we do were we, as in the US for the NASA missions, what we've done is you actually have what's like a measuring tape. So Light Sail did a version of this. NeoScout's doing this. The next follow-on solar sail mission, Solar Cruiser, is also doing something similar. What we explore in our diffractive solar sail deployments is also this. You have these booms that are like, when you think of a measuring tape, you know how you play that game where you try to see how far you can get the measuring tape out without having it kink? That's exactly what they're doing. They're pushing it out. They're pushing out these booms, and
except there's no gravity.
There's no gravity, so it doesn't fall. There are reasons why the booms kink, and it is an issue. And that's when you think of like regular solar sailing, it's novel. It's, solar sailing in general just lets us, you have massless infinite propulsion, and I don't think you can get better than that, right? There's just stuff that they always talk about the tyranny of the rocket equation, right? The traditional rocket and propulsion will not get us to some of these really unique orbits that we would like to explore for science observations when we're talking about the sun, solar weather monitoring. The biggest thing that we always harp on, and if you go, I think there's another picture, but if you actually think about it, we don't know what the sun looks like on the poles, right? There's been Ulysses is the only one that's actually been to a higher inclination out of the ecliptic, and it didn't have a camera, so we don't actually know what the solar poles really look like or how to characterize them. So how do you get to those high inclination orbits in a heliocentric orbit to do was like, wouldn't it be cool to have like a whole weather monitoring system that's 4 pi steradians around the sun? How do you do that, right? So solar sails is how you could do that, and you could maintain it because you're never going to run out of sunlight, right? Especially if you're going around the sun. So that's
now you've mentioned a diffractive solar sail a couple of times.
Yes.
What is the difference between a diffractive and maybe a more traditional solar sail that we're familiar with?
Right. So if you kind of see this picture, hopefully it doesn't come up too blurry, but when you think of solar sailing, so how does solar sailing work, right? You have light is also a wave, but also a particle, and don't think too hard into that. Right? That's the the way I always think of it. But when you it comes from the sun. You get this sunlight in a broadband spectrum. Those light particles hit a reflective surface and bounce off, and that, because it's a particle, it's like when you hit a pool ball and the other bounces back, right? Same situation, only it's with light particles. Now you get this very small force, like nanonewtons of force, right, from this one instance. But if you have large thin areas, you can actually start to generate a pretty good thrust that's it's low thrust, but it's high ISP, so it's high efficiency. So you can do these slow maneuvers around, and you can kind of see in the picture to the right, where you're doing these like orbits where you're cranking up. You can also crank in. It's not like traditional propulsion where you do, okay, we're doing a burn here, we're doing a burn here, we're doing a burn here. No, it's constant thrust that, again, is massless and infinite, right? You're never going to run out of propellant. So diffractive is a little bit different. So when you think of diffractive sails, when reflective sails are obviously just they look like tinfoil, to be honest. They look like huge pieces of tinfoil. They're a bit more complicated than that, but that's what they look like. When you talk about diffractive sails, I don't know, if you're in university physics or whatever, one of the things they have you do is like shine a laser through a diffractive grating, right? And you see the laser like spread out nice in a cool pattern, and it diffracts the laser, right? So you're taking that principle of, okay, well, we're going to change the momentum of whatever this light is hitting because you're changing the direction of the light from an incoming angle. But now you're not bound by the laws of reflection, which actually you can only get to so high of efficiency because, if you think about it, it's like a sail into the wind, right? So you're not going to be able to go anywhere unless you're tacking back and forth, right? Like a diffractive sail, though, you can actually take that force and you can tailor the grating. And this is something that Dr. Swartzlander at RIT won the NIAC phase 1 and not phase 2, and now we're trying for phase 3 to explore this concept where you can actually tailor these optical gratings and this huge sail to direct that force however you want, right? And you can make it way more efficient. I think we were finding like 30% more efficient. So that gets you there faster,
wow,
better, and cheaper. And that's all we like to hear.
Yeah. And it gives you like a wider range of angles that you can be compared to your light source.
Yes. And that's the biggest part.
That's
too. So
really interesting.
It actually takes a lot of the issues that you have with attitude control in solar sailing. Solar sailing should be everywhere right now. There are technical issues that are hard to overcome. You're talking huge floppy things in space, right? No one likes that. But yeah. That's hard to control and it's hard to implement, and it's very mass sensitive. So you can only get so big on your sail because then you start to get into deployment issues, right? You see just how much it takes to put that entire sail into a little shoebox. Now imagine doing that on a 1,400 meter sail. You're talking the size of a football field, right? You need.
But I could definitely imagine some future when I can imagine this future where all spacecraft are equipped with a backup solar sail that's ready to go. And so when the reaction wheels inevitably fail, they can deploy the solar sail. It's kind of like a sailboat. You have to have an oar or some backup method on your boat to be able to, if your main motor dies, you can still use something else. And to have a solar sail that's pitching in can give you a much wider range of missions that you can accomplish, more science that you could do, as long as you're willing to be patient for the sun to just keep contributing to your mission. I think it's great. I'm such a huge fan of solar sails, and this is great.
Yeah,
you guys have
if
gone
they're
this far,
diffractive, they
and
look like
you
this.
might, and it should be running on. Was that you this time, Pamela?
There I am.
Okay.
Sorry.
Yeah. Apparently Pamela's having tornadoes right now. Again. I'm going to stop complaining about a little bit of snow. Because they had a tornado tear up an Amazon warehouse near her house.
I can't hear Fraser.
Yeah. All right. We've lost her again. Marie can't hear me. But Moya can hear me. Carolyn can hear me. Yeah. Oh, she's muted, and Marie's muted. Yeah.
I was being polite and muting myself.
Technical issues. Thank you for bearing with me on that.
No, it's not you. This one is probably this time it's probably coming from the source at this point.
But I will say the cool thing about the diffractive solar cells is they look like a rainbow, because it's like when you have a CD, like in this picture. So if you got that backup sail and it's if you deploy it, you get a fun show too.
That's so great. Yeah. I haven't done much digging into these diffractive sails, but now I'm totally obsessed. So I'm absolutely going to check this out. Well, Amber, it was great to have you join us and talk about your research. If people want to keep an eye on this for themselves and follow your work, what's the best place to go?
So we've published quite a bit, me and Dr. Swartzlander at our team, and through Johns Hopkins. I have a LinkedIn. Look up my name, Amber Dubill. But you can also look at NASA Innovative Advanced Concepts. You will see, and look up diffractive light sails. You'll also see a lot of really cool other out there ideas that are just Titan submarines and putting people in biochambers and all this stuff. So if you're into that stuff too, I'm a huge proponent of the NIAC program, and you can find us on there, and hopefully you'll find another point to us too. So
yeah, me too. All right. Well, thank you so much, and take care. Good luck with your mission.
Thank you.
All right, Moya.
Hello. Can you hear me?
I can hear you.
Fantastic. Let's talk about Neptune. A study came out just this past Monday in the Planetary Science Journal, and researchers were claiming that Neptune is apparently about 14 degrees Fahrenheit cooler than it was in 2003. So it's cooling down, and we don't really understand why. But I'll give you a little bit more background information. The researchers were primarily at the University of Leicester, and they compiled more than a decade's worth of mostly infrared data on Neptune. They had thermal images from ESO's Very Large Telescope, both of the Geminis, North and South, Subaru, Keck, and they also had infrared spectra from the Spitzer Space Telescope, all from between 2003 and 2018. They were measuring specifically the temperature of the stratosphere, which is the layer of the atmosphere right above where all of the active weather is. And you can see in this graph the downward trend of temperature over time. And this cooling is unexpected because Neptune's southern hemisphere is in summer right now.
Right.
Yeah, and
Why, you know, based on the weather talk we've already had today, I think it seems perfectly normal now.
right, Neptune is also undergoing human-made climate change.
Yeah, exactly.
So I actually didn't realize, I had just never thought about this, but Neptune has seasons just like Earth does because it has its own tilt. It's very similar to Earth's. It's 28-ish degrees instead of 23 and a half. But they have an even more circular orbit than we do. So their seasons, just like ours, are based on the amount of incident light, the amount of like 90-degree light that you're getting from the sun, even though they're much further away. But they are about 30 AU, so 30 times farther from the sun than Earth is, and Neptune's period is 165 years. So each of these seasons last about 40 years. And yet the global average temperature of Neptune has dropped really quickly in the last 20, way faster than we would expect given how long the seasonal cycles are on Neptune. And the story gets even more interesting because not all parts of the planet are cooling down. More recent data from Gemini North in 2019 and Subaru in 2020 reveal that Neptune's south pole, the temperature there has actually increased by 20 degrees. So if you look at this graph on the far left side of it, which is so the x-axis here is breaking it up by latitude of the planet. So the far left side of the graph is the South Pole. And you can see that the 2020 line, which is the purple line, is way hotter than the 2018 line. And then as you go to different latitudes, moving towards the right of the graph, the 2020 temperature line gets a lot lower than the 2003 line. So there's really interesting stuff here happening. The temperature is like 20 degrees higher at the South Pole than it was just a few years ago. And scientists have never seen this kind of polar warming on Neptune before. But we also have only had the technology to reliably measure Neptune's temperature for like not even one of its whole seasons. So maybe this warming actually isn't that strange. But if it is, there are a few, actually, even if it's not strange, there are a few possible explanations that they put forward in the paper. One is that maybe this is just a seasonal change that Neptune has, and that there are influences, that there are changes in the chemistry of Neptune's atmosphere that would affect the way that heat gets transported across the planet, making it easier to cool the planet down. Another possible explanation is that it's tied to the 11-year sun cycle. They did find a weak tentative correlation between solar magnetic activity and the number of visible Neptunian clouds high in the atmosphere and the temperature in the stratosphere. So they didn't explicitly tie this connection, but I think what they would say is happening is that the solar activity somehow increases cloud coverage on Neptune, and that when there are more clouds, that it can create a cooler atmosphere because not as much sunlight is getting deep into the clouds. So yeah, they don't really know why this is happening, but cool stuff is happening on Neptune.
Why this is happening is someone else's problem.
Yeah, it's one of those classic papers of, we have made this observation and it is beyond the scope of this paper to explain what's happening.
Yeah, the researchers have hypothesized. Yeah, exactly. Have speculated wildly, but we have no idea what it is, and this is not our problem. Yeah. Yeah, we'll let the rest of you figure this out.
I've written a paper like that for sure.
I have discovered something really interesting.
Maybe they could just say,
yeah.
That's an even better one. Yeah.
We'll leave it
That's
as an
awesome. Very cool. Okay. All right, Marie-Liis, you've seen the rest of the team take a crack at it. Now it's your turn. Which story do you want to do first?
Okay, I hope you hear me fine and we have no problems this time. Because
that's it. All of our internet problems are over.
It's been quite a while, right? I had to refresh my browser and I was lost for a bit, but okay, let's give it a try. Okay, so I would like to talk about the Magellanic Clouds first.
Do it. We're ready.
Okay, if I freeze or whatever, you can just, wave your hands, just give me a sign so I don't end up speaking for like 10 minutes and then I will find, okay, no one heard me, fine. Okay, so the large and small Magellanic Clouds, despite their name, are galaxies orbiting the Milky Way. And there is new research led by the University of Surrey in England that found synchronized peaks of star formation in the galaxies. So astronomers examined 5 peaks in this star formation rate of the small Magellanic Cloud. And this was found to match similarly timed peaks in the neighbor galaxy. So I mentioned that the 2 galaxies orbit the Milky Way, but they also orbit each other. So one of the Magellanic Clouds triggers star formation in the other when they pass near each other. And this indicates that there has been tidal interaction between the 2 that has played an important role in their evolution. And these peaks have been traced back to at least 3.5 billion years. So they have gone back in history quite a bit. And the study was made by using this, again, great acronym, because astronomers do love those, we all know. It's called SMASH, which is for Survey of the Magellanic Stellar History. And this survey is based it's carried out with a 4-meter ground-based telescope in Chile. So fascinating stuff.
So, I mean, I had understood for the longest time that astronomers weren't even sure that the Magellanic Clouds were captured by the Milky Way's gravity and were on an eventual collision course. But with Gaia now, do we know that they are doomed?
So the paper here, I'm not sure about Gaia's approach on this, actually, because I skimmed through this paper, and that mentioned that the galaxies are like drifting further apart now. Mm-hmm. Maybe it's because of their orbit. So basically, we don't expect any of those peaks anytime soon now. But I'm not sure about the interaction with the Milky Way, though.
Right.
It's a good point, because I'm pretty sure that the newest data release of Gaia will definitely have a say in this as well.
And so are they then orbiting one another and then just in some strange interaction? And I wonder how close they get to each other.
Well, I mean, this is probably a number of light years that's incomprehensible. I saw these numbers and they were just like hundreds of thousands of light years, and it was I didn't process this number myself, to be honest.
And so what is the kind of impact? Like when these galaxies get too close to each other, what do they do to each other?
Yeah, so I think that these tidal forces affect particularly the smaller galaxy, and I think there could even be like this kind of, it depends on how close they get, but definitely kind of collision which starts to play together with dark matter, with the interstellar medium, so the different gases. Okay, I see. Do you still hear me?
Yep, everything's fine.
Okay, perfect. I saw something kind of laggy. Sorry.
So like when I think about, say, the Large Magellanic Cloud, it has the Tarantula Nebula. It has one of the most active star-forming regions that we can see, like more than we have nearby us in the Milky Way. It is way more active with way more stars than even, say, the Orion Nebula. And I wonder if that star forming activity, this is one of those results from these interactions between the large and small Magellanic Cloud, that you can get that, if you have a whole galaxy collide through your galaxy and you get that collapse of material, then you get these monster star forming regions.
Yes, you're absolutely true. I think now that the astronomers have identified those peaks of star formation and they have traced back how many billions of years ago they happened, they could match then those famous star formation regions with those peaks, because it absolutely makes sense for these beautiful, beautiful star formation regions with like insane shapes of gas to be the result.
Yeah.
So
yeah.
I think that's a detail to also try and find in the paper, which is really interesting.
Very interesting. All right. Well, we've got about 10 minutes left, and I want to get to the argument portion of the evening. So, so why don't you present your second story, and then we'll get into it. So, what else has happened?
Okay. So this is a short story, and it's about the first commercial crew that arrived to the International Space Station on, I think it was on April 9th. So the launch was on April 8th, and the crew is staying at the ISS for, I think, 8 days. So they're midway now. And it's special because it's the first privately funded mission to the ISS. And it's called the Axiom Mission 1. I hope I don't pronounce it too bad.
That's right.
So it's operated by the company.
Oh.
What company?
What company?
Now I need to know.
So, from what I understand, they paid $55 million per seat for the 4 astronauts to go up there, and NASA is charging them $35,000 per night per person for room and board on board the International Space Station, which seems kind of cheap when they're spending, but that legitimately covers all of their food, all of their water use, all of their air, all of the energy they're going to use, their internet, and as well as safety and insurance and so on. So it's, I guess I should wave. I'm supposed to wave, right? Marie-Liis, we can't hear you. Goodbye. So what do you guys think? Moya?
So these are private people who paid a bunch of money to go up into the International Space Station?
Yeah.
But they took a mountain of science projects with them and are mostly doing science for the entire time.
Okay. They could have paid that money to send scientists up there, couldn't they?
No, because then the scientists would have to run through the National Science Foundation or NASA, and there'd be this long rigmarole. But if you just want to make liquid telescope space, then you gotta pay your $55 million a seat and send up your own guys. And the science experiments sound great.
Mm-hmm.
Like I mentioned, they're building a liquid telescope. They're testing out a liquid telescope in orbit, which could end up being 100 meters across in the far future, filled with some kind of viscous fluid that will become a telescope lens, which is really neat.
Mm-hmm.
So you've got a whole bunch of these experiments, but some billionaire is paying for flights for a bunch of his friends to go to the space station, to show up while the astronauts are doing their work, hiding out nooks and crannies to stay. What do you think, Carolyn?
Well, yeah, there is a lot of scoffing about rich guys flying in space, and that's kind of what caught my attention first. And without reading about the experiments, I mean, that's kind of justifiable to hear people. So what I did is I immediately went to social media and started reading, and there's, it kind of falls down on two sides. People are all for commercializing space. Others are like, no, we shouldn't be, letting rich people fly up there. And in truth, we've been commercializing space for a long time. We have. You look at it one way, you realize that we've had involvement of commercial enterprises since the first day that somebody had to build a spacecraft. So this is not a new idea. That's a generalization. It hasn't changed. There are many, many companies involved in space. I wrote a book 2 years ago about space exploration, and I'm sure that there's probably twice as many as I wrote about in the book. And you have the whole new space movement that's predicated on, having younger, nimbler companies kind of jumping past the old, aerospace concerns. I also had, seen a lot of conversation about how there's really two kinds of commercialization of space. There's like space for Earth, which is where you have companies involved in creating goods and services that are, in space, but we use them here on Earth, like drugs and, that sort of thing. And then there's space for space, which is the space tourism, asteroid mining, building habitats, all this kind of stuff that is really sort of still in the future. So when I see people complaining about, there's rich guys going to space and it's commercializing it and that's how somehow ugly, I just have to say, look, we've been commercializing it for 60, 70 years now. So let's get real here.
Yeah. I mean, I don't really care. I think that
I just want to go to space myself, but I don't have $55 million.
That's what I don't like about it. That it makes it puts this barrier in place where if you want to be an average person, like a regular person who's not connected to research or NASA or anything, you have to be rich to experience this. And I love that. Yeah.
Marie-Liis, we were waving. But it didn't work.
It didn't reach me, unfortunately. Once I had stopped telling the story, I realized you were all frozen.
We're all frozen.
I just thought you were very thoughtfully listening to me.
So what do you think? So I finished off your story. I presented the rest of the information. But what do you think? Do you think that it's a good idea for private astronauts to go up to the International Space Station to use the resources of that aging fantastic machine, and yet they're paying for the right? Or do you think it's not a good idea? What do you think?
I do support just increasing the access to the space station, because we know how incredibly difficult it is to become an astronaut. Like, I mean, from the selection process, how many people do actually reach the very top and who will actually in the end be selected for our crewed mission? It's just such tough odds to beat. And it's really nice to see some other ways for people to make it there.
Rich people to get there.
That's exactly. That's currently the problem. But it's nice to see that at least there are these kind of like open access competition where we saw people competing on social media to get the chance to go. So I hope to see more of these opportunities where, the access will be just not only for the rich people, as you mentioned, where the price of the ticket is not the only thing that determines whether you can go. But I feel like it can be a start to something good.
I mean, like seeing Inspiration 4 and seeing like Dr. Cyan Proctor got a chance to fly, like how could that be a bad thing?
Yeah.
And so I think that as long as these billionaires are getting a sense of the backlash that is waiting for them, that they can try to at least democratize and give lots of people a shot at doing this in this time while they're funding the flight. I don't think we're ever going to get to a point where just your average regular person can pay for a flight to space. Like it's never going to be less than $1 million.
And currently also, I would like to mention that still, okay, we saw Inspiration 4. The people that ended up going were still, above average in every sense. They were really impressive people who had a lot of training, like, I don't know, pilot licenses and all kinds of background, I think skills.
I think though, but like merit, having the skills and getting a chance to fly, I mean, just it's another way of funding astronaut flights, which I think would be great. But if the only way that you get to do it is because you have a lot of money, that just feels that just makes you feel.
Yeah, I agree with you. It's like,
just don't come back. You can stay
we're
there.
just
if you want.
witnessing a joyride. I mean,
did you see the space perspectives release that came out today? They're the balloon company. And so they're doing stratospheric balloons. They're going to go up to like 30 kilometers, but it's like this nice, big, cushy lounge that you sit in, you sip your cocktail and go to the point that you see the curvature of the Earth. And it's going to be much cheaper, like in the tens of thousands of dollars, as opposed to in the hundreds of thousands or millions of dollars. And I would way take a 5-hour flight to the edge of space in a nice balloon over 3 minutes in a vomit comet.
Yes, that sounds really nice.
Doesn't it sound great? Yeah, I think Space Perspectives is going to run away with this. Yeah.
They actually presented about that. They actually presented about that at the Suborbital Conference a couple of years ago. It was just like in infancy.
Yeah. It sounds great, and I think they've nailed it. That's, I think we want to get that overview effect, and I think that's why you want to hop on a Blue Origin, or that's why you want to get in a Virgin Galactic and take that quick flight. And a little bit of weightlessness would be terrifying, actually, I think. So
but you can get that on Earth. The weightlessness.
Just fall off something. Just jump somewhere high.
Yeah, I also bet there are safe ways.
A 10-meter diving board.
Chambers, yeah.
Yeah. Jump off a 10-meter
diving board. Fraser, look at it this way. We can practice sending the billionaires, right? And that's where everybody learns how to take care of people in space. Then they work out all the kinks, and then other people get to go.
Let the billionaires be the guinea pigs.
Yeah,
yes.
That was so brave. They're so brave.
I just really, really hope that something will, kind of stick with them from this trip, as you mentioned, the overview effect. That's my only hope with these people with immense wealth going, that maybe they will care more about this insane chain of people who are all working, like with these minimum wage salaries.
Yeah, I mean, it does really feel like we should get as many human beings to experience the overview effect as possible. Like there's something wonderful that happens to their brains and they come back changed people. I mean, that or mushrooms or something. I don't know.
One is much cheaper than the other.
Think about when William Shatner came back.
Yeah, he lost his mind. He was so excited. Yeah. Jeff Bezos wouldn't even let him just finish. He was so stoked on what he experienced.
He went anyway. He's still terrorizing archaeologists for what they're saying about his show.
Wait, what?
Oh, that's a different cup of tea. That's just William Shatner he has a show about archaeology, but is not making real archaeologists happy.
Right. Right. Well, that clearly we're going to have to dig into that, but this is not here and not now. All right. Well, you know what? We've reached the end of our hour. So, Marie-Liis, welcome again for joining us here on the Weekly Space Hangout. Sorry for all the connectivity issues. Pamela, I'm sure we'll sort out the tornadoes next time. But if people want to follow your work and stay in touch with what you're doing, what's the best place to do it?
Okay. So first of all, thank you all. And I'm sorry for losing the connection on my part. There's definitely a lot to learn. So I'm very active on Instagram, and I have a blog as well. So I'm very sorry you have to type out my complicated name, and my handle is by Marie-Liis, and my homepage is also called bymarie-liis.com. So you can find all my social stuff there, as well as a blog just completely dedicated to astronomy, also useful for astronomy students and enthusiasts who want to start out in the field. Maybe, I don't know how to type it out into the chat, or maybe Nancy can take care of it.
I'm sure it'll be in the show notes.
Okay, perfect.
Yep. Fantastic. Awesome. All right, Moya.
Hello. You can find me on Twitter at GoAstroMo. I encourage you to check out my podcast, ExoLore, EXOLORE. I just put out an episode about the Wheel of Time universe. So if you like that show or that book series, check it out. And
my wife just finished the 10th. She finished them all.
So all like 14 million
all
words.
14 million. Yeah, exactly. Yeah.
It's so long.
Yeah.
Maybe she would enjoy the episode. And
Okay. And that's on your podcast.
On my podcast,
Okay,
Exolore.
all right.
And I
Yeah.
have a book coming out in August. You can pre-order it now. It's called The Milky Way, an autobiography of our galaxy.
Fantastic. Carolyn.
You can find me at thespacewriter.com, where I have my blog, and I'm on Twitter at spacewriter.
Perfect. And of course, I'm Universe Today on all the things. I've got 2 interesting interviews coming up tomorrow. Early in the morning, my time, I've got Surjit Rajendran, who is a particle physicist, and we're going to be talking about what comes next for dark matter. And then tomorrow at 5 p.m. my time, I've got a guy named Dr. Paul Sutter, and we're going to be talking about the W boson.
Ooh.
So this new interesting discovery made about the W boson, Paul and he's going to explain it to me because he's my go-to guy for all things particle physics. So, but it'll be great. And Marie and Moya, maybe, I don't know if you remember, Paul was one of the co-hosts of the Weekly Space Hangout. And then he got too busy, he got too famous, which is what happens to all of you, by the way. This is just a temporary stop on your way to fame and stardom. So enjoy
PhD,
the ride.
Book, fame.
Yeah. Yeah, you are absolutely
You're on track.
Yeah, you're on track, Moya. You know it. Come on.
Thank you to the Weekly Space Hangout pipeline.
Yep. Yeah, exactly. All right. Well, thank you everyone for joining us today. Thanks to all my co-hosts. Couldn't do this without them. Thanks to everyone watching us both on YouTube and on Twitch. Thanks to all the moderators. Thanks to Nancy Graziano for keeping everything organized. And thanks to Pamela for going above and beyond, literally fighting tornadoes to bring this show to you this week. So thank you, Pamela. And we will see all of you next week. Thanks, everyone.
Bye.